Alright, Dalton's law of partial pressures. The pressure of a mixture of gases is the sum of the pressures of the different components of the mixture. So the total pressure is equal to gas 1 plus gas 2 plus gas 3 and so on. So the total pressure is the sum of our partial pressures, and it depends on the total moles of a gas of particles present, no matter what the gas is. So in this problem we have helium and we have oxygen gas. And those are being pumped into a tank, and our final volume is 5 liters. So we're calculating the partial pressure of each of these gases and then the total pressure. So the first thing we've got to do is figure out our pressure of helium. So we know the volume of helium, the temperature, and we know that it is now at 5 liters. So we can use P1, V1 equals P2, V2, because our volume's changing and our pressure is changing. So it was 1 atm. And when it was at 1 atm, it was 46 liters. Now that it's at 5 liters, we don't know our ending pressure. Now we're going to do the same thing for oxygen. We have 12 liters at 1 atm. And again, it's going to be at 5 liters. And that gives us 2.4 atm. So we found the pressure of each gas. Now we just need to find total pressure. So total should be the pressure of helium plus the pressure of oxygen. We know our helium and we know our oxygen. And that should give us 11.6 atm. With Dalton's law, you're going to have to know about mole fractions. Because remember, the total pressure is the sum of the partial pressures and depends on the number of moles present. So mole fraction is represented with chi, which looks like an X. And so it's moles of whichever gas we're trying to find the mole fraction of over total moles. We can also say, because moles is directly proportional to pressure, that the partial pressure of our gas over our total pressure will give us the mole fraction. Or rearranging that, partial pressure is equal to the mole fraction times total pressure. So our mole fraction is given as 0.7808. And we're trying to find the partial pressure of nitrogen if we know total pressure. So we need to use the equation. We need to use the equation. Mole fraction is equal to P1 over P total. Or partial pressure is equal to mole fraction times P total. We know our mole fraction, and we know total pressure. So then we get 593.4 torr. Alright, go ahead and read this problem. Pause the video when you've got your answer, restart. Alright, so the first thing we've got to do is figure out our mole fraction of oxygen because it didn't give it to us. So we know that we have 1.77 moles of oxygen over total moles. We add these up. That's 14.2. We have a mole fraction of 0.125. We can multiply that by our total pressure, and oxygen has a partial pressure of 0.615. B says, what would happen to the partial pressure of oxygen if another gas was added to the container? The partial pressure should remain constant because our mole fraction would increase and the total pressure would increase. So the ratio should stay the same. Total pressure, if we add another gas then, would have to increase because we have another gas. So total pressure would increase, as would our total number of moles. An important aspect of Dalton's law is when we collect gas over water. Anytime you're collecting a gas over water, you're also going to have water vapor pressure. And we would use the water vapor chart at the bottom of your notes to calculate or to figure out the water vapor pressure based on the temperature. So in the diagram we have zinc and hydrochloric acid reacting and we're producing a gas. This hydrogen gas is going to be going through the tube into the water, and here's the end of the tube, and so it floats up. We have our hydrogen, but notice we also have water vapor molecules. This is what we refer to as a wet gas. So in this one, it says that it was decomposing potassium chlorate. We were making oxygen. It was collected by the displacement of water. So when I read that, I know I'm going to have P total is equal to the pressure of water and the pressure of, in this case, oxygen. Total pressure was 754 torr. To figure out our pressure of water vapor, you're going to have to look and see at 22 degrees Celsius what the water vapor pressure is. Should get 19.8. And so now we know our pressure of oxygen. But it doesn't just want to know our partial pressure of oxygen. It also wants to know how much KClO3 decomposed. Which means we need our equation. So I go ahead and predict the products of potassium chlorate. Going to produce oxygen and our metal chloride. Since we're converting between substances, we do need it balanced. And the only way to convert between our substances is if we know moles. Well, we know the pressure of oxygen, the volume of oxygen, we know the temperature it was collected at, so we can use Pivnert to figure out our moles. Our pressure, though, is in torr, so we need to convert that to ATM. And so our moles are 0.0259 moles of oxygen. And finally, we can do our mole-to-mole ratio. Converting that to grams.